This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Hello everyone, joining us around the world, and welcome to the Distinguished Lecturer Webinar Series. Before we go any further, my name is Kerry Cosby, and I'm the Chapters Manager here at the IEEE Computer Society. I oversee our more than 500 professional and student chapters around the world, and manage our Distinguished Visitors Program. Before we get started, I'd like to get a couple of housekeeping tasks out of the way. You can ask your questions in the Q&A panel. Dr. Chakrabarty will answer as many questions as he can following the presentation. The webinar is being recorded, and slides and recording will be made available after the webinar. Today's lecture will be Machine Learning for Medical Image Analysis Demystified. I'd like to introduce our speaker. Amlan Chakrabarty is a full professor in the A.K. Chaudhary School of Information Technology at the University of Calcutta. He's an M.Tech from the University of Calcutta and did his doctoral research at the Indian Statistical Institute, Calcutta. He was a postdoctoral fellow at the School of Engineering in Princeton University. He is the recipient of the prestigious Department of Science and Technology Government of India Boys Caste Fellowship Award in Engineering Science from the Indian National Science University, also the Indian National Science Academy Visiting Faculty Fellowship, Japan's Society for the Promotion of Science Invitation Research Award, the Erasmus Mundus Leaders Award from the European Union, and the Hamid Visiting Professorship from the University of Cambridge, and the Siksha Ratna Award by the Department of Higher Education of the Government of West Bengal. Dr. Chakrabarty, I'd like to pass the floor to you.
Thanks, Kerry, and good day to all the participants all over the world. Thanks to IEEE Computer Society for hosting me and giving me the opportunity to address all of you. So my today's lecture will be how we can use the various machine learning techniques, what are some of the insights of the machine learning techniques which are well applied in the domain of medical image analysis and visualizations, and that is a very interesting domain for the present research as well as for developing business use cases. And obviously in the present era of COVID pandemic, we are moving towards trying to find solutions, and there are some solutions and some good achievements have already been done where they have used the machine learning and deep learning techniques. So my today's lecture will be just some insights and some use cases, and I hope that you all will be enjoying this lecture. So to start with, we will have a brief overview of what is medical imaging. So medical imaging is a modality or is a form by which we try to visualize the different components or structures of the human body. And the advantage of the medical imaging compared to the other detection and diagnostics process is it is non-invasive, and it is often used as a first step of screening in many of the medical diagnosis applications. But when we look into the imaging as a set, the operations what are done in imaging, it's a really a wide range of operations what we can see, and it incorporates operations in the domain of radiology, tomography, endoscopy, microscopy, medical photography. So you can understand the amount of things which gets into the amount of specializations and the variability of this domain of medical imaging, and that's why it is so challenging and so interesting. So there are various procedures, and the procedures for medical imaging varies from the different modalities, which I will just speak out in the next slide, and also depends on the particular disease, its prognosis, and the way it is being visualized by the radiologist and the medical practitioners. So as I have already told that it is a variety, so medical imaging itself consists of a wide variety of methods and techniques, and fundamentally, depending on the way we capture this medical image, it is being termed as the imaging modalities. We have number of imaging modalities because our body is composed of various forms of structures, both in shape as well as in functions. So each of the modalities are well tuned with a particular type of structure, with a particular functionality of the particular structure, or also depending on the information we need to gather, we can use more than one modality to analyze the depth of the disease in a particular individual. So that's why each of the modalities, and as well as multiple modalities, helps to know our deformity, or to know the disease diagnosis in a better way. These modalities, as I already told, capture different structures at different levels, at different scales, and that's why it can be from the body cells to the muscles, to the tissues, to the organs, and in some ways it can be a combination of organs too. So if you look into the entire space, it consists of various forms of imaging modalities, and accordingly they are also being named on the process of the capture or the basic source of energy which is used to capture the information. Like we can have the computer tomography, which is normally called as CT images. We can have magnetic resonance imaging, we commonly termed as MRI, positron emission tomography, which is termed as PET, and then ultrasound, X-rays. These are very common modalities, and also we can have a fusion of the modalities, which is very popular nowadays, because some of the modalities are good for some structures, as you can see in the figure given, that we have provided a list of organs which can be well screened by a particular modality of images, and sometimes we need to have the information coming from modalities, because one can give you the structural information and one can give you the functional information of the same organ, and that's called the fusion. Yeah, it's a really a huge domain. So I can speak all that means in terms of medical image processing. I can give a seminar or a talk only on one modality. Similarly, for the doctor's point of view or the radiologist's point of view, they can spend hours on studying that what are the deep physical phenomenon which or the medical assumptions and medical analysis they do for each of the modalities. So we can easily think of the huge amount of information, or the huge amount or the variation in the image information, which really makes this particular medical image analysis a very interesting field. So as we will be discussing on the computation of this medical image medical images, we have to have an idea that what is the process of digitization, or what is the standards which are followed in digitization of these image informations. So fundamentally, the entire system can be coined as a picture archiving and communication system, which is also commonly abbreviated as PACS. And what PACS consists of? So PACS consists of the various ways we can acquire the data from the different types of image acquisition systems, like CT, like PET, like X-ray, like MRI machines. And then these images are archived because they can be they need to be analyzed, both for the current patients as well as they can be used as history information to develop your models, to develop your computational techniques. And obviously for the radiologists or medical practitioners to analyze these images, or to visually see these images, as well as to give their own decisions, they require the display workstations, which actually take the data from the storage devices, and they show this data to the respective medical practitioners. And obviously, to have a support of all this, we require a very robust communication infrastructure. We can connect the devices end to end, so that they can be well stored and well communicated across the users. Next, so this is the the picture or the figure demonstrates that what are the various stages, or what are the various components of a modern PACS systems. Similarly, as we are mostly focusing on image analysis, there is a standard way or standard database system, which is known as Radiology Information System, or RIS, which actually documents or stores all the activities for a particular radiology image, and also it tries to connect with the other information management systems, like health information management systems, which can also help to generate a patient history, as well as also some sort of analysis in terms of the other diseases which are not related to radiology. Also, they can connect the radiology information system to those studies also. And this is an integrated system which is integrated with the PACS. Now, when I am speaking about all these type of imaging modalities and the image storage, obviously we have to know that there is a specific standard of image communication, and the way the images are exchanged between the various parties in this ecosystem. And that particular format is actually called a DICOM format, or digital imaging and communications in medicine. So they can be exchanged between multiple parties who are working in different. There may be doctors who are working with different types of disease study, and there may be this exchange may be between multiple parties, like it may be between a doctor and a particular patient also. So when we get the data of our own images from the test scans, what the format I receive is a DICOM format of my scans. So this is a standard, because you know that as there are so many varieties, the standard is very much required, so that the images which we generate, which we store, and which we communicate follows a specific standard, so they can be well processed and well analyzed. So this is the exchange scenario or information scenario in the domain of DICOM. The format or the way this is being conveyed is the DICOM, and that is standard across the international arena. Now I will discuss with the the specific motivation of this talk, which is actually using the computational techniques for image analysis and visualizations, which actually can be also coined as the more used term, more commonly used term, which is called computer-aided detection and diagnosis. So, and that is abbreviated as CAD. So what is a CAD? So what CAD does is actually it is type of that it is a set of software tools, okay, which helps the radiologist to analyze the image and to give insights of the image. So first level of analysis may be only trying to know that whether deformities or not. Okay, that is called or a sort of the location of the deformities also. That comes mostly in the form of detection. Okay, and then further we can go further and we can try to analyze this deformity in a much details with more specific feature analysis, and that leads to the diagnostic view of this, and that's okay, and that's why the CAD can be called as a detection and diagnosis. It is not that every CAD combines both of these, but we can club both of these under the term of CAD. So that's the goal. So how CAD helps us? That helps the doctors or the radiologists because it gives a lot of information, okay, in a very automated process. And how much automation we can do, that depends on the way we can develop our algorithm using the machine learning or deep learning techniques, and that's where this techniques helps us. So more and more automated way of detection and diagnosis we can do, more it saves the time of the doctors or the radiologists, and it can serve more number of patients in a given amount of time. So basically, it is the image interpretation in various forms. So as I told that one form of CAD is computer-aided detection, which is a sort of a screening radiology, which is also termed as screening radiology, which actually identifies the deformity and tries to localize the deformity, so that the next set of process, either it is a clinical process or it is the next way of computer aided next step of computer aided diagnosis can also be performed. Some good application is that means it detects and it helps in fast screening, and also it tries to give the doctor some marker of the possible regions in the image which show certain abnormality. Okay, for example, as this is a chest X-ray image, and this is the circle which is being marked here. You can see there is a circle marked, and that is a patch of tuberculosis. So CAD detection will exactly accept this particular X-ray image, and through its algorithm will mark this particular region and will tell the doctor or radiologist, hey, I have found out a tuberculosis patch here. And then looking into this, the doctor then can suggest a clinical procedure, or it can be further analyzed through the diagnosis, computer-aided diagnosis procedure. So now, if you look into what is computer-aided diagnosis, it is more called as a clinical radiology, because it gives you the clinical insights of the detected regions. And these clinical insights are also termed in terms of the computational methods are called risk assessment. So how this helps me? So suppose, this is the scenario what I have predicted. So you see that if you give my computer-aided diagnosis the various forms of images, Okay, it gives a sort of score or a sort of grade to the particular image or a region of the image, and how it helps the doctor. It helps doctor because the doctor now can be can see this particular score generated by computer-aided diagnosis tool, and can be very sure that, hey, if I do a biopsy of this particular region as the score is very high, I ought to get some results, right? And so unnecessary biopsy that means is not at all done in the case of, or not at all recommended in the medical procedure of cancer detection. So this type of scoring or this type of diagnostics to computational analysis of the image can help the doctor in finding out the regions which needs more exploration, and actually leaving the regions which doesn't require much exploration based on the particular diagnostic scores. So this is the CAD and what we are trying to develop, or what we are trying to teach in the terms of machine learning and deep learning, how we can develop efficient methodologies to develop the tools in this particular domain. So as I have already uttered the terms machine learning and deep learning, I am just jumping into that particular techniques, or those particular techniques, and that is a fantastic scenario of machine learning is. So what is machine learning? Machine learning means that a machine which can run intelligently in a way, and this intelligence is not a static intelligence like normal computation program, where the intelligence is based on a particular logic or an algorithm, and that algorithm is static. In the case of machine learning, it is a continuous learning process by which the algorithm improves itself. Okay, improves by losing also in some cases. So an algorithm which actually generates error at some point of time can actually recover from the error and can give you the fantastic results. So this entire scenario is coined as a learning process, and that's what it makes so interesting, and that makes it very able and increases the adaptiveness of the algorithms to solve the complex scenarios what are normally handled in the case of medical image analysis. So machine learning is actually how as the father of machine learning, Arthur Samuels, spoke that without explicit programs, a computer can actually do some fantastic job. Okay, and that is the using the data. So using the data, it knows that this data has led to good results, and this data has led to bad results. So using this particular insight at the start point, it can differentiate between the data items, or can categorize the data items in its own form by developing something which is called a machine learning model. And then the term performance, which was very well spoken by Tom Michel, and what he told that these learning models improves the performance with experience. So performance means that, suppose in the terms of medical image, that whether I can localize the deformity in the chest X-ray, or the tuberculosis patch in the chest X-ray within a resolution of this pixel, with a resolution of say the 20 pixels, or whether we can generate a detection procedure which can detect a sub-centimeter long nodule. So this may not be done at the first run of your algorithm, but slowly the algorithm improves the performance for a given particular task, and that's the way slowly and steadily the algorithm becomes a very strong algorithm which can go into a very high level of precision or a very high level of performance for a complex task. So there is multiple strategies, and we cannot discuss the strategies in this particular lecture. But classically, but just to give a brief overview, they're categorized as a supervised, where we use a training data or a good bunch of label data to train our models. Another category is known as unsupervised, which is where we don't have the labels, but the model learns through a sort of exploratory analysis and tries to identify data in terms of a sort of comparison metric or a distance metric, and tries to associate and de-associate data with one another, and that forms a cluster, and that is called a clustering technique, which is a very well-defined, well-used technique in the domain of unsupervised learning. The third technique is called reinforcement learning, which is very different from what we do a supervised learning. It is normally used because when we don't know a good strategy which can work, and we also require we don't have the time to use a sort of training data. Either it is not there or it is not very good. So how we can actually build a intelligent system which can work, and there in the case of reinforcement learning, we go for an model that goes with a sort of a benefit model, and it is a greedy approach by which it tries to take the best path, either a best path for predicting a particular result, and tries to prune out the rest of the paths, and so in a ultimate process, so prunes out the path which gives the lesser benefit or the penalty, and ultimately this model chooses the best possible path or the strategy which can predict a result very correctly. So as you know, that I have just given a very overview of the machine learning techniques, because the major focus of this lecture is towards deep learning. So if you see the progress of the machine learning techniques in the terms of this image analysis and visualization, obviously there were no machine learning technique. Initially, people used to just take the help of mathematical and statistical measures, and tries to identify the structures, and mostly these were very granular level, in the sense that they were at the pixel level comparison. So I can always compare an image X and an image Y, and I can tell that, okay, this image X is similar to Y or not similar to Y by comparing the pixel to pixel. But this is a very time consuming, and this cannot work for some of the complex structures, and it cannot give all sorts of information what we want. So the next step up was actually machine learning, which became very natural from 1990s, and people started using different types of supervised learning like SVM, like base classifiers, and there we use different types of the data which are available used to generate the training data, or maybe the clustering technique to find out the useful patterns based on the features. The domain of deep learning, which is now heavily dominating this particular scenario. This particular scenario is something what I can say is that it's a deep learning domain in the present scenario, which is just going all around. Okay, and deep learning gives a very good way of not using the features which have been collected and then passed on to the classifier. Rather, the deep learning strategies can extract the features itself and can build a very well-tuned classifier which can perform very complex tasks. And that was not that is not possible in many of the conventional machine learning algorithms. So this is the scenario. As we can see, that 1970 to 1990, before the machine learning, it was more the low-level features in terms of the mathematical functions and computations. Then obviously supervised techniques like SVM-based classifiers, all this came into existence, and then from 2010 or 2012 onwards, we have the era of deep learning, and a lot of the deep learning techniques are now being well used in this particular domain of medical image analysis. So before going into the deep learning architectures, which are very well used in the domain of medical analysis, I will just give you a brief overview of what is deep learning. So the term deep learning is based on the deep neural networks. So these neural networks are nothing but hierarchical layers, which actually tries to generate an inference, which may be the ultimate abstraction from your data, with repeated operations or repeated transformations in its various layers. And how it works in a very beautiful way, in the sense that it tries to get the features at the lowest level at the initial stage of the network, and then it tries to build a sort of confidence, okay, from these values which are generated in the lower layers, and tries to enhance this confidence to reach to an abstraction which may be a prediction, and that's the way it works out. So an example given, given a set of images, you can first detect the edges, okay, and then you can find some sort of feature between the edges which represents the nose or the eyes or the lips of a face, and then finding in the information the features of nose, lips and eyes exist, you can determine that's a face. So you see that the way our neural thought process in the biological world works out, the deep neural network tries to imitate in a similar fashion, and tries to develop the computing engine in that form. So the output, we actually try to generate a prediction, and that prediction can be a quantitative value by itself, or in the most common cases, it is a sort of classification result, what we try to expect. So as I told that this particular form of computation is a sort of imitation of the biological network, which starts from a small neuron which does a simple function, but stacking the neurons and actually adding various functions in the various layers of the neuron. This stack of neurons works a wonder. Okay, and that's what our brain system also does. So in the brain we have the different functional regions, and each functional region actually abstracts the data, or actually generates a different sorts of outcome in the different layers, and all these outcomes are ultimately aggregated to form the final decision. So if you look into a bigger depth of what it is just imitating the various lobes or functions of our brain, okay, in some scale, okay, and trying to do a sequence of transformations and okay, and sequence of feature based scoring, okay, to develop a particular observation or a prediction for a given input, right? Okay, that means and obviously this network is costly, right? This is costly because it involves a lot of computations and it involves a lot of stages. And so, but as we know that now the storage as well as computation power for hardware are enormous, and they have scaled up to a great height. And now these deep learning algorithms in the present era of cloud and GPU are very well suited to do this, because the entire gamut of functions are mostly the cost is mostly to develop the network. Once you develop the network, then the network actually gets settled down and can run very fast. So the resource requirement and all these things at the present scenario are also very well applied, or they can be well achieved, and that's why it is getting more popular. Second, the most important why it is getting popular is that in the case of classical machine learning, what we try to do, we try to do our own observations in terms of the feature space, and the feature space are created independently to the classifier, and then the classifier works in the way we supply the features. So in some cases it can work excellently, but in many of the cases, if we don't understand the feature well in the feature space, then classifiers can do very bad. And in some cases, when the data itself is complex, to generate the feature space or to abstract the feature space itself is a very complex problem. Feature based, in this case of deep learning strategies, we have the feature extraction and classification goes in sequence. So the first stages of the network are basically extracting the features and actually building your feature space in a very automated or robust way, and then the feature values are passed through a network which works as a classifier, and this classifier gives a result. So this particular model is robust in that sense, and can adapt to the training data very well as the feature extraction is automatic compared to the standard machine learning models, which can work for a particular set of data, but can fail if we change the data or change the context. So that's also the reason why deep learning is getting very popular. So now, if you see the layers of the deep learning, we look into the layers and we see that they consist of layers which starts from the convolution. These are nothing but filters operations, and these are filter operators are done in multiple times. So there are multiple filters which operates on the image in a spatial form, and these are nothing called convolution kernel. Each of these convolution filters results to an outcome of the convolution, and then this outcome is passed to the next type of layer, which is the pooling layer, which actually generates a sort of representative value out of a window of the value. Suppose I don't know whether you can look into the window. So if you see there is a window, and from the window we take the maximum. If it's a max pooling layer, it's a max pooling layer. We take the maximum value from the window. Okay, so how it helps us? It helps us in two forms. One is that is the most dominating value which is being generated in the filter in the filter outcome. Secondly, as we are taking the value from the window, a little shift within the window will not matter because the maximum value will remain the same. So what it does, it gives you a very robust approach which is independent of some sort of spatial variation in a local form, and also it gives a priority. It gives a priority to those values which contribute well in the final outcome.
Dr. Chakraborty, can I interrupt you for just a moment? I think there's a bit of choppiness in your... Yes, thank you for turning off the video. I think that may help it.
Yep. Thank you. Yeah. So the next stage of these values which are collected by the pooling layer is the activation function, and this activation function, though there are a lot of activation functions are available, like sigmoid, like tanh, but the most common activation function which is being used is known as a ReLU. Okay, and this ReLU is nothing but a nonlinear function. Okay, if you see this is the function which is ReLU. So the ReLU function works in a way that any value given to this particular function, will be a sort of max between x and 0, right? It is a max between x and 0. So what does it actually mean? It actually means that suppose I have some negative values, and so those all values are normalized to 0, and whatever value I have, that will have an effect. Whatever positive value I have in my outcome, that will have an effect in the next stage. So it preserves. So it doesn't saturate, okay, and also it is very sensitive. That means it actually sensitive because it actually doesn't work the sort of indecision which works in the other types of function which are like sigmoid and tanh. So if you want to see all together, okay, in the all together we see that okay, it is a sort of the stages which can be taken as a convolution layer followed by a pooling, and then there will be multiple stages of this convolution and the pooling, and then we have a vector. Then we have a feature vector generated which can be a vector, and then this vector is put to a network which a multi-layer network, and that gives you a classification score, and from the classification score you can well classify or predict your input data. So this is a basic architecture which is used in many of the image processing applications, and I will just tell you that this particular architecture or the CNN is the most popular architecture in the terms of medical image processing. What I mean to say is that it is not that everybody uses CNN, but most of the networks what we use in the case of medical image analysis is some variety of this CNN. So the way I can actually control, or I can for a particular problem I can try to think what will be my CNN. These are the questions. So what I will do, how I will define my convolution layer. That means how many convolution filters I will have, or how many layers I will have. That depends on your feature space, or how much feature exploration you want to do. Whether you want to do very low level features, or you can just stuck with some higher abstraction of features. So depending on that, you can fix your number of layers in the convolution filter, and then the pooling gives you a sort of subsampling. So how much data you want to condense and want to pass to the subsequent layers, so that your decision can be well handled. So if you go to a high granularity, it means that you're working with a large amount of data, and if you go with a larger window size, it means that you are squeezing the data much. And so whether you are focusing on local variation more, or you feel that local variation is not so high, it is more the global features which dominates my results. Accordingly, you can set your pooling layer size. Okay, and the window stride means that so you hop with this particular pooling. So what is your hop length or hop distance, right? And then comes the classifier, which is the fully connected. The number of neurons gives you, that means how you are generating the ultimate score. If you require a lot of transformations from your initial feature vector to generate the score, you require more number of neurons and more number of layers. But if you have that, and also if you have more number of classes, you may require number of neurons. So depending on the classification problem, you actually tune that. So now, saying all these things, we can easily understand that why this deep learning technique dominates or can be well used, because it is automated. The feature extraction is done automatically. It responds well to the change in the domain, and sometimes we can do the transfer learning also here, and so all this exploited fully makes this network a very robust and can handle the complex problems which goes very deep in terms of feature extraction and classification. So if you see the medical imaging tasks, what can be done? Obviously, classification is one of the core tasks where we try to tell that, hey, this is a malignant, or this is a benign lung nodule. Okay, that means I can identify whether there's an anomaly or not, and that is the way we classify. We detect a particular region, or localize a particular region in a big structure, and that is called a detection. And we can tell that, hey, there is something is there. Some deformity is there in this particular location, which is detection, and obviously this classification and detection itself can involve segmentation, which means that churning out a region of interest, because ultimately in the medical analysis process, it is not that we or the doctors look into the entire image. A doctor is interested in a part of the image which is called a region of interest, and if we can analyze that, whatever first we need to do a segment it, and then we can extract the features, and then we can classify that. So that is segmentation is a very fundamental thing we have to normally do in the case of image analysis, medical image analysis. And obviously, I will not speak much, but registration is also a very interesting domain, because I've already told you about multiple modalities of image, and the registration process helps you to understand So how we can map the images, or how we can take a common information of the images which are coming from multiple sources, multiple modalities, or maybe at multiple point of time. So we can compare the images, and we can also take the information in a combined fashion. But before all these things, what we need to have is register the images, which means that they are being mapped in a common coordinate system. Okay. So So now the challenges. So said all the things are very interesting in the terms of medical image processing and image analysis. There are some challenges. The challenges is obviously the data size. It is, we all know that the medical data, availability of medical data is still a big challenge, and if you want to start with a medical image analysis problem, you have to get in connect with the medical house, and obviously you may find that the actual patient data are less than the data which is available with the medical house. So how you build your machine learning model which can able to work or can detect those type of patient data. So that's a challenge, and to start with, most of the times we don't have the annotations of the labeling of the data, so we don't know that labeling here means that a doctor can give me a guidance that, okay, look, that this level, this particular deformity tells that this is a sclerosis. Okay, this is a necrosis of the lung, but it requires a doctor to label this information for a particular image data, and we all know that the time of the doctor and the availability of doctor to doing this work is sometimes very less, and so unless we have this label data, it's very difficult for us to develop our machine learning models. Similarly, that means there are a plethora of models. Which model I will start with, or which model can give me a result within a short amount of time, is still a sort of judgment we have to take, and that is a lot of challenge we have to face, because your model can fail very badly, right? And so understanding that what will be a good model, or what type of approach you will take to develop your model, is obviously still a challenge for a lot of the application domains. Next is a training, because everybody is interested on the outcome. So what your model does with the test data. Okay, no user is interested to spend time on a particular process which doesn't give outcome, because training doesn't give outcome. So training establishes the model or stabilizes the model, right? Once the model is stabilized, now you can apply this model on unknown data, and then your outcome which is required by the users can be generated. So how we accelerate this training? Okay, that's a very big thing to do, and then is the result interpretation, which means that the way we want to show the result may be computationally very good, or we can understand it computationally, but how it affects the doctors. Okay, so how it affects the doctor. So that's a very challenging thing, because when we work with the doctors, we tell that, see, doctor, I have come up with a very beautiful classification technique, which gives you this score. But it should be a form that the doctor can accept and the doctor can take the decision. Right, and that's called result interpretation, and so that's the good way. That's also a challenge, and at this point you need to sit with your doctor, with a medical collaborator, and try to find out what is the best form, what is the best visual form or statistical form the doctor wants. So the way the entire process works is something like, that means you push the data, build your model, and then model gives you the result, which needs to be in a form which can be well visualized. So data planning, model building, and visualization of the result, these are the very three important aspects of building your system which can effectively work for medical image analysis. So there are certain techniques to handle the data, because as I have told you that that the techniques like that means the data, the scarcity of data. So the scarcity of data can be well handled by a technique called data augmentation. In the case of data augmentation, what we try to do, we try to synthetically or in a simulation process, we try to enhance the training set by incorporating some sort of statistical deviations, okay, from your initial sample set, and through these deviations we can generate a large sample set which have different values of those deviations, and that can well work as your this augmented training set, and there are very good reference paper which are available in the public domain, and you can look into the paper which is published in MICAI 2015 by Roth et al. The other way we can do is that so training so data less means you cannot run your network for large number of training samples. So how you can work then? So the way it is worked, it is called a transfer learning. So in the case of transfer learning process, what is adopted is that, okay, you don't have a data in your domain because your domain is medical domain, and maybe for a particular disease which is rare or which is not available in your medical, the images are not well available in your medical house. So what you do, you actually train your network, initially you train your network, which is called the pre-training of your network, with a data set, with an image data set which is in a different domain. It can be ImageNet. ImageNet has a large number of image classes. Okay, and you can actually train your network so the large number of features which ImageNet gives. Once you train this particular network with your data, with large big set of data, then what you do, you actually try to do a fine tuning of this network with a small available data set with which means the feature set which is available or the features which can be extracted from your smaller data set can now fine tune this network and can make this network very well built for your specific application, though you have a very small amount of training data. Right, and you can also have there are a plethora of published material which shows that how transfer learning can be well used in medical image analysis. So now I will go with some of the example networks what are very well explored. So the most well-known network in the domain of medical image analysis was proposed by Ronenberger in 2015, and it was a winning network or winning algorithm in computer-aided detection challenge, and this unit is a form of convolution network, because if you see this network, you see that there are convolution filters which are being defined at the first level, and so the numbers which you look into, numbers have some significance. So the number at the bottom of this what represents the size of your data, and the number at the top of the line represents the number of convolution filters you use. So if you go through the network, you will see that there is a compaction of the data, the contraction of the data in this particular path, which is called the contraction path. You see the data size decreases, okay, and your filters are also extracting or working on the smaller size of data in each level. So what it tries to do, it tries to achieve here is actually it tries to reduce the locational information. Okay, it tries to reduce the locational information and tries to enhance the enhance the feature information which is more global, right? And that's the way we this unit works, and it is called a unit because you see the contraction path is one half of the U, and then there is there's an expansion path, okay, which actually expands the data, right? And this expansion path is nothing but a concatenation of your convolution output in the peer-to-peer layer. So this particular line, what you see between an input side and then an output side, it tells that this line means that the convolution data of this layer is being fed in the corresponding layer in the outcome. Okay, and that is a beautiful strategy has been developed, and this unit is very well used in a lot of segmentation applications. Due to limitations of time, I cannot give a detailed description, but this is just an overview of the salient features of unit, which tells that it is a network which goes through a compression and expansion of the data in the convolution layers, and then it goes through a connectivity between the peer-to-peer layers, which actually goes with a concatenation of the data of the compressed layers, and it gets merged with the expanded layers, and that forms the two arm of the U, and that is what is called a unit. This is another form which is very interesting. This is called a generative adversarial network, and this is an approach in your deep network by which we try to find that which features are more important. So the features which are more important can actually distinguish an object very clearly with an object which is very similar. So I can always make a fake object corresponding to one object, but this fake object will actually lose out some very detailed information which is there in my real object. So now this generative adversarial network, or commonly known as GAN, utilizes this particular strategy, which actually tries to find out that which features are actually discriminating features, and try to remove out the features which are not. And in this process, it actually reduces the network size of the system in a very great way, and can work to give you a very good results in some of the very complex problems. This is another very well referred paper which was published in 2018, and this is a first of its kind technique where the researchers Li Q Daw and his group have shown that, hey, I can use a CNN with a little bit twist. The twist here is that, first of all, it works in a 3D, which means that it works on a multiple scan images. Not only that, it works with the different types of scales, okay, different types of modalities. So these 4 layers, what you see in the extreme left, are the different weighted images that you want, T2 water weighted images of an MRI, and then you find that in different images and different input, we have used the different scaling size of the image. Okay, so the focus of this network is that you can get some features in low scales and some features in the high scales, and then you try to do a merging of features which are strong both in low scales as well as in high scales, which can able distinguish a particular structure in a particular given image, and that's what is being done in the segmentation of a vertebra of a spine, which has been reported by this group in 2018, and that is again a CNN model, but which has been modified with multiple pathways and using the multiple scales of image. Next example is one of the example which one of my student has recently achieved. It was basically generating the Gleason score, and this Gleason score is basically the score for which is given for histopathy images after the biopsy of the prostate, and this is a histopathy image, and Gleason score actually tries to classify the severity of this particular of the particular cancer in this in the particular tissue. So what we did here is that we had a very less number of training samples. So the method we tried out is actually transfer learning, and we did a transfer learning with a set of images which are available in a very well-known data set called MS-COCO data set, and we trained our network with that data set. Okay, use the transfer learning with a small data set given by the MICAI challenge. So this was a MICAI challenge in the last year MICAI challenge, and we successfully developed this transfer learning based technique. And that means our method was performing good and with a good level of accuracy as per the expectation, and hence our method was listed in the MICAI, in the MICAI rated techniques in the domain of segmentation and classification. So that was one of the ways. So you see that how transfer learning helps because our domain was very our data was very less in the particular domain. The last network what I want to state is obviously very interesting, which is called the COVID-net. This COVID-net is also a variation of the class of the fundamental CNN, but it is a different workflow. It works with a model which is called the PPEX model. If you see the image, it's called the projection expansion and projection expansion pattern, and it also have some connectivities which are long range connectivities. So they try to acquire the spatial information in a very better way and in a very lightweight form, and this model or COVID-net is now getting very popular as a first screening strategy for our COVID patients because the chest X-ray can be done with a very ease, and they can be analyzed with this particular COVID-net type of analysis, and they can be classified as COVID or non-COVID, or they can be defined as a risk of COVID or non-COVID, and this is getting really popular for the chest X-rays, and people are trying this with the CTs also. Right? And if you see that this particular COVID result, which is being done by the group of Linda Wong, I think it is the Waterloo group. They have very well utilized this particular architecture, which is new, which is defined by them, and it has shown promising results of applying these deep nets for the COVID chest X-rays. So the conclusion, what I mean to state to all of you is that obviously this is a very challenging domain of research and computing, and it has a great promise. It has a great promise in the screening the initial images. So helping the doctor to localize the deformity it can help in pre-surgical assistance or pre-surgical modeling. It can help to reduce the biopsy. That means it can help for developing the training modules for the 2D doctors. Actually, this was one of the scope of one of my PhD student, where we developed this particular CAD tools and extraction of this particular CAD tools based on machine learning. It can help the doctors to train them when they doesn't have specialized doctors in the initial level of the study. So it's basically data driven. It can actually adapt to different new things and new circumstances, new disease domain. It is very well adaptive. Okay, yeah, adaptive, and obviously it has a very good way, or it shows a very good path to go on a continuous path of improvement, and the outcome of this can be very well used by the community, not only the doctors but the social community at large. So last but not the least, actually, I have a group of students who are all PhD students. I am not. There are interns also, but I'm trying to just let you know about the work we are doing. So we have students who are doing in multiple domain of activities in designing efficient CAD techniques for lung nodule detection, techniques for finding the spinal deformities on the X-rays and CT. We are also working on the deep networks for brain segmentation. We are working on MRI images for spine and for extracting or localizing the deformities using deep networks. And also we are working on 3D reconstruction and visualizations in the domain of spine, MRI, and CT. And so that's all from me to all of you. And I hope that I try to give you a scenario of deep learning and machine learning in the space of image analysis, and I think this is a fantastic field, and I'm open to collaborations to work with some of you if you are interested to join me. Thank you all.
Thank you, Dr. Chakrabarty. That was a wonderful presentation. I know we've gone a little bit over our time, but if you have some time, I'd like to read some of the questions to you.
Yeah, sure.
Okay.
Please go ahead, Kerry. Yeah.
Here is one question we've gotten. Is it possible to aggregate instances for similar classes when matched in training and testing split, and how to justify it? Which algorithms can we use? Any examples?
Okay, so it is a good question. So having the training and test examples are really sometimes it is very easy, and sometimes it is very challenging. So as I've already shown that there are some strategies where we can have a large amount of training data, but which can be very different from what we have as a test data, and so sometimes we try to split the training data itself into training and test, but then what we also have to look at whether there is an imbalanced class problem or not. I haven't discussed this in this particular perspective, but you have to have a sample distribution. That means in the training, which well reflects the test data. Okay. And then only your classification can give you accurate results. If not, if your training data is biased, or if your training data doesn't contain the samples, then the only procedure that you can do, either you do some sort of sampling technique like oversampling in the domain where you have less data, and undersampling in the domain where you have more data, or you can also go to data augmentation. So this actually that means you have to look into a data set, and accordingly you can take this technique. But these are some of the thumb rule techniques what I tried to mention. Okay, yeah.
This next question came early in the presentation. It was, what are the modalities?
Okay, so there are a lot, and it is obviously, that means I can tell that I might be not knowing all of them, but the modalities are basically the way the information is captured. Suppose if I'm telling that okay, I am capturing the X-ray. So X-ray, we all know it is a sort of electromagnetic energy, which actually there is a plate, and so your bones have calcium, so they absorb that energy, and okay, other body parts which are basically watery, they don't absorb, so the rays passes, and so in the photographic plate at the back we get the impressions of bone and non-bony area. That means the same, but this X-rays are very static. It's a sort of gun which points to a particular region of your body. But if you actually move this around in a three-dimensional way, and both your detector and your source moves around the body, it becomes a city. But again, the city and the X-rays are good for the structures which are hard. For the structures which are soft, like most of the brain tissues, you require to find the level or the water content or that way we'll try to find the softness of a tissue. So when we use the MRI, which is called the magnetic resonance imaging, where the water molecules actually generate or actually radiate a sort of energy in response to the magnetic energy or the magnetic field where it is placed, and based on that, it's called a tomography image, and you can reconstruct the image. So you see that depending on the organ, depending on the type of the information you want to capture, you have to take a modality. Okay, and the ultrasounds are good examples where you have a non-rigid type of file. So there are something which are not rigid, and their ultrasound can work well. And when you have a lot of mass in a water soluble or in a fluid sac, all these techniques might not work. Only ultrasound gives you a good idea about the depth and the structure of the organ. So I hope I have answered a bit of the question of how we choose the modality and what are the modalities are there. Yeah.
Okay, very good. This next question may be fairly broad and take a bit of time, but perhaps you could shortly tell us about optical coherence tomography.
Okay, so this is something what we try to do from the source of the images. Okay, so there are, that means I am not so much knowledgeable in terms of the image sources in that way, but what I see in my image information is that means the optical incoherence can lead to a lot of these noises. Okay, and these noises are very difficult. Actually, we have worked with a paper where we have tried to find out the Rician noise in the MRI, and we know that if we can know the source model of the noise, it is very well to denoise that image. But in the case of this type of medical image process, the medical image acquisition, it's a complex interplay between your environment, between your instruments, and between your body organs. So it is a sort of complex interplay between that. And due to this interplay, there are a lot of variations occur in your image capture, right? And there are a lot of type of noises which can generate. And then what you try to analyze in terms of image analysis, that if we can categorize that, okay, this particular noise might be for this particular noise, might be for this source, and then we try to generate a particular source model and try to cancel out the noise. And that's what we do in the terms of processing. But in terms of the source and all these things, I'm not a very expert on that particular part. Yeah.
This next person asks if you can explain RL with practical examples.
Okay, this RL means it is reinforcement learning. Okay, okay, that's a very good question. So, so reinforcement learning, as I told, it is a sort of, that means it is best explained in terms of games. Okay, obviously we have to take that in terms of medical imaging, but to make a good explanation, I will try to explain in terms of games. So what happens in the games is that if you are doing a sort of supervised learning, in the case of supervised learning, you take the data that means from your domain, or you train your system. Now, in terms of game, you can train your system in terms of the best moves your best player in the circuit have performed, or maybe a set of best player. Now, can you generate a gaming agent beat the best player? So the problem in a supervised learning is that your system can perform best at best as that your training data, because training data also tells you that, hey, look, that this is your input and this is the expected outcome, okay, for a set of input which generates. But sometimes you may tell that, no, I don't, the outcomes in the training data, what is there, I'm not satisfied. Whether I can do a self exploration and I can do something which can outperform that is being generated in my training data, right? And also it works in some cases where you don't have a good amount of training data or a confidence on the training data. So in that case, what you try to do, you try to adopt all possible strategies at first. Okay, you can explore all the sort of tree branches, and then you try to prune out the tree branches which doesn't gives you a good accuracy, or gives you a very low accuracy, and you attach a sort of penalty to that, and you try to progress in that path which actually gives you a good accuracy. Okay, and that's the way how the game engines are developed. And that strategies are well used in terms of your segmentation and detection and risk predictions and reinforcement learning in medical images too. Yeah.
Very good. This next question is the integration of ECG signals and image possible for cardiac studies?
Oh, that's a fantastic question. So that is called a fusion. So ECG signal is a time series data, and image is a spatial information, right? And when you are doing capturing the information for the objects like heart and lung, they are non-rigid. So this image also has a sort of temporal shift. But the features what the images gives, okay, are basically the structural features, okay, and this gives the functional features, okay, the ECG in the time, and this is a very wonderful way of actually getting the both structural and functional feature in a particular time domain analysis. Right, and that means I didn't work in this domain, but I have just started working on using capturing of the lung sound information with one of my PhD student. But I think this is a very good domain, provided it is cost effective. Okay, because provided you can do at one point of time, you can do this chest imaging, either it is a CT or an X-ray, and you do the ECG time signal, and then you generate a type of fusion model. I will check the research in this domain, but this is a very interesting domain, and I think that the time series and the spatial data can be fused, and it can turn out to be some good insights. Yeah.
Very good. The next question is, how can deep learning convolution networks extract image features automatically? And the person notes that they know only 3 basic image features: color, shape, and texture.
Oh, okay. So yeah, I have a little bit squeezed up the convolution network because within the time I cannot if I give a detailed explanation in the convolution network, it will take a lot of time. So what convolution network does, you try to just take it in a very simple way. So what is a filter, right? A filter is trying to maximize something and minimize something. So given data to a filter, okay, so the outcome will maximize some input, which I tell the filter has accepted that, and will minimize certain inputs, and I tell the filter rejected that, right? So you develop the filters based on your features. Obviously, when you take standard CNNs like UNet, like VDGNet, like ResNet, like DenseNet, okay, they have their predefined kernels of convolution. Okay, it doesn't hamper you to change or define your own convolution layer and build up your entire model. But the only thing is that you need to find out your information is spatial, obviously texture, intensity pattern, frequency variations. All this can be considered or can be taken, and also there are some sort of statistical measures, right? That means whether mean or maybe variance, and all these things can come up. So these are features in a gloss, right? And then you know that there are filter kernels which can actually sweep over your image in small windows and can evaluate all these features in that window, or rather generate the feature values. So a particular kernel is defining a feature that is adding to a feature space, and the value what the kernel is generating is nothing but the value corresponding to the feature what the kernel is meant to. So what you actually require, you require the kernels for your feature, and the kernels are good if it can generate outcomes which will tell that the feature is maximized or minimized. If from the outcome you can tell that, okay, yeah, in this region these features are high, and in this region these features are low. So that will be the way your kernels are developed, kernels are created, and each kernel consists of a certain stage of weights and a set of operations involving the image data which can do that for you. Okay, and that's all how the concept of the filter and convolution network comes into play. Yeah.
Very good. The next question is global pooling always a good choice?
Yeah. So we are pulling depends on your window size and your stride. Okay. So if your window size is 2, your stride will be automatically 2, right? If your window size is 4, you can then go to either 4 or either 2. So more the window size, more is your global. And if you want to devoid of more and more spatial locality, then you can use a larger window size. But if you are in an optimum or in a sort of spatial locality where you don't want to overlap the spatial regions in an image, then I think you have to adjust your window accordingly. So global pooling is only fine if you are only selecting a gross global features, but that will not be a good way to understand a medical image, because medical image have lot of spatial variations in a particular image, and that is not a very well suggested technique in the case of medical image. So normally the window size are not very large in the case of your medical image analysis. Yeah.
Okay, this next question is, how do you think deep learning or alternative machine learning model is helpful in solving medical image registration problems?
Yeah, that means if you ask me frankly, if that means in a very straight way, that means one of my PhD student is working on the registration problem, and we are still using the concepts of fuzzy and soft computing techniques, right? But registration is a very, very obvious phenomenon when we try to work with images from multiple sources. Okay, if you want to build our database itself, not only doing any processing or detection, just to build our database, we also have to have the database where all the images are well registered, and actually seeing the variability in the registration process, the hunch feeling is that it should be a very preferable for a deep learning network, right? But if you ask me, I have mostly worked still now on the domain of segmentation and classification in the domain of deep learning. But wherever there is a large variation in the information, and it's very difficult to find out the patterns which gives me a good accurate result, deep learning, though costly, though maybe overworked in some cases, you can tell me, but if I have the resource, I will tell why not. Right? If I have the cloud resource, if I have a good GPU resource, I will tell why not. Let's try it. Okay, yeah.
All right, very good. We've still got a lot of questions out there, and I wish we could get to all of them, but our time has passed. So I do want to thank you, Dr. Chakrabarty, for your presentation. It was great. I think everybody enjoyed it. I apologize to everyone for some of the audio problems that we've had. Hopefully we were able to solve those in the last part, and hopefully we won't have them in the future. But I'd like to thank everybody else for joining us today. In addition to the Distinguished Lecturer webinar series, we also offer Build Your Career webinar series that focuses on business soft skills such as communication and presentation skills, career transition, interviewing tips, among others. The next webinar in the Distinguished Lecturer webinar series will be on the 11th of June at 11 a.m. U.S. Eastern Time. Katarzyna Wach will cover quantifying the quality of life of smartphone-centric humans via human-centric methods. Our next Build Your Career webinar will be on the 18th of June at 11 a.m. Eastern Time on What Everybody is Saying by Elsa Velasco-Paul. She's the founder of the M&E Group. Registration is now open for these, and we'll be sending all of you a link to these future events, along with the slides and the recording of this webinar. Again, thank you very much, and Dr. Chakrabarty, this was a great presentation. We really enjoyed it.
Thank you, Kerry, and thank you all.
All right.
Have a great day.